morning, students. My name is Chaitanya, Physics faculty at Shakthi International School. In this video, we are going to learn about an important topic of class 11th from chapter Thermal Properties of Matter. Thermal Properties of Matter. And the topic name is Thermal Conductivity. Thermal Conductivity or Thermal Conduction. Thermal Conduction. Okay. So thermal conduction is a process in which heat will be transferred, and heat will always transfer from hot body to cold body. We know this because energy always transfer from higher potential region to lower potential region. Lower potential region. Okay. So now we know how do we define a hot body and a cold body. We know the degree of hotness or coldness will be given by the temperature. From that we can analyze whether the object is hot or cold. Always heat transfer will takes place from hot body to cold body. Okay, and this thermal conduction happens in metals or solids precisely. Okay, this happens more in solids. Only why in solids? Because in thermal conduction, okay, the atoms or the molecules which are present here, due to their excess amount of energy or heat, they vibrate from their equilibrium position, and when they vibrate they collide with the next particle, transferring the energy, and the next particles will start oscillating and they will transfer the energy. In this way the heat conduction will be happening. Conduction of heat will be happening. Conduction of heat without change in the equilibrium position of the particles. Equilibrium position of particles. So this happens in solids. Now experiment shows that if I am taking a body of, let's say, a rod of length L, this is having a length L, area of cross section A. If it is maintained at two different temperatures, let's say it is T1 and this is T2, and if I am assuming that T2 is greater than T1, then heat will be conducting. We write that heat Q per unit time. Experimentally it is shown that it is directly proportional to the change in the temperature difference. Okay, this is heat current we are talking. Heat current. Okay, I will show you an absolute analogy between electric current and heat current as well. We define Q, heat, with the letter Q. Okay, we denote it with the letter Q. Now heat by time will be heat current. What they are observing is, in a steady state, okay, the current which is passing, the heat current which is passing at every point is always being same. And the first and foremost important conclusion is the heat current is more if the temperature difference is more, and the heat current is less if the temperature difference between those two ends is less. Okay, not only this one, another experiment proved that heat current is inversely proportional to the length, and moreover heat current is directly proportional to the area of cross section, which is, if there is a more area of cross section, then heat is transferring faster. If there is less area of cross section, then the heat is transferring slowly. So with the different shapes and sizes of rods, they did this experiment and finally concluded that the heat current Q by T is proportional to A into delta T divided by L, where L is the length of that rod. If you are removing this proportionality symbol, we have to add in a constant, and that constant is what we are calling it as thermal conductivity. It is called as thermal conductivity, K. Okay, A into delta T divided by L, where K is called thermal conductivity. Okay, now this heat current, which I represented from now on as H, where H is equal to Q by T, can be written as K into A into delta T divided by L. Now this thermal conductivity depends on few factors. It is actually the characteristic property of the material. Okay, it depends on the material. Okay, if you are trying to give the units of K, okay, how we can write the units of K? K can be written as H into L divided by A into delta T. Now H is heat current. You can write the unit of it as joules per second because it is Q by T. Unit of heat will be in joules. Unit of time will be in seconds. Joule per second into length is meter divided by area of cross section is meter square into temperature is Kelvin. So these two gets cancelled. We can write the unit of K to be as joule second inverse meter inverse Kelvin inverse. This will be the unit of thermal conductivity. This will be the unit of thermal conductivity. Okay. So now, since we know, okay, that thermal conductivity can be given in this format, if you are trying to analyze it with the heat current, with the electric current, you know what is the reason for current to flow? It is the potential difference, delta V. In the same way, what is the reason for the heat current to flow? H. It is your delta T. If there is no change in temperature, then no change of heat will be happening. No heat current will be flowing through it in a steady state. Okay, in a steady state means, okay, the major difference you have to analyze here is you have to understand the steady difference. Okay, see, let's say at this point the temperature is T1, at this point temperature is T2. Let's say at this particular point temperature is T3, at this particular point temperature is T4, at this particular length. Now, this T1, this T3, this T4 and this T2, okay, all have their own individual temperatures. It is not necessary they all have same temperatures. Okay, according to steady state, it is necessary that the temperature at this particular point should not change with respect to time. Change with respect to time. It should always be the same. That's when we can take that heat current is same. Okay, Q1 by T1, Q2 by T2, Q2 by T2 is equal to Q3 by T3. Okay, it should always be the same. Heat current should always be same. Okay, that is what we are calling it as a steady state. Now, why we are actually I'm explaining about you this one is, we know V is equal to I into R. In the same way, we can write here delta T is equal to H into some kind of resistance. This is resistance for current flow. This will be thermal resistance. Thermal resistance. Now, we know what is conductivity. We have a formula. From that formula, we can write H is equal to Ka delta T divided by L. If I want to bring it to this format, I can write this one as, okay, I can write this one as, if from here you can write I is equal to V by R, in that way I can write H is equal to delta T divided by K L divided by Ka, where L divided by Ka is representing the resistance. Okay, is representing the resistance. The resistance, thermal resistance now can be written as L by Ka. This is the formula for thermal resistance. Okay. Now, with the help of this thermal resistance, what we can do? Okay, let's say two metal rods are connected in series, or metal plates are connected in series. There will be a series connection and there will be a parallel connection. You know that when two resistors are connected in series, effective R equivalent can be written as R1 plus R2. In the same way, when two resistors are connected in parallel, the effective resistance of this, the equivalent resistance of this, can be written as R equivalent is equal to 1 by R equivalent is equal to 1 by R1 plus 1 by R2. In the same way, if you are having two rods which are joined in series, okay, and two rods which are joined in parallel. Now in this case, these two rods are joined in parallel. This is having an area of cross section A1, area of cross section A2. It is maintained at a temperature T1. This is also maintained at a temperature T1. This end will be maintained at a temperature T2. This end will be maintained at a temperature T2. Now here in this case, the area of cross section is same here A, and this is also A. The length of it can be different. This is L1 and this is L2. But in this case, the lengths are same in both the conditions for both the rods. Now this might have a conductivity K1, this might have a conductivity K2. Here in this case, it might have a conductivity K1, this might have a conductivity K2. Now to find the equivalent conductivity, we can use this logic. From the resistance, it will have a resistance R1, it will have a resistance R2, thermal resistance. In the same way, this will have a resistance R1, this rod will have a resistance R2. So you know, since they are connected in series, R equivalent can be written as R1 plus R2. Since these two are connected in parallel, R equivalent can be written as 1 by R equivalent can be written as 1 by R1 plus 1 by R2. Now substituting these values, okay, where R1 can be written as L1 by K1 A1 and R2 can be written as L2 by K2 A2. In this equation, you can write R equivalent is equal to L1 divided by K1 A1 plus L2 divided by K2 A2. Since I am explaining you that areas are same, I can write R equivalent as 2L, or precisely L1 plus L2, not 2L. It will be L1 plus L2 divided by K effective. K effective into A is equal to L1 by K1 A1 plus L2 by K2 A2. So if areas are same, they can get cancelled. So finally the expression of K effective L1 plus L2 divided by K effective can be written as L1 by K1 plus L2 by K2. From here you can find the equivalent conductivity, okay, of the combined rods. In the same way, when they are connected in parallel, you can write this one as K effective into A1 plus A2 divided by L, since the length is common, is equal to K1 A1 divided by L1 plus K2 A2 divided by L2. Since you know lengths are same, you can write K effective is equal to K1 A1 plus K2 A2 divided by A1 plus A2. So this is how you can find thermal conductivity, effective thermal conductivity or equivalent thermal conductivity. You can call it as equivalent thermal conductivity in parallel, and this will be the equivalent thermal conductivity in series. Okay, you can write 1 by K effective if you want to further analyze it as 1 by L1 plus L2 into L1 by K1 plus L2 by K2. So this is how we can find effective thermal conductivity when the rods are connected in either, when the rods or the plates are connected in either series or in parallel. Hope you have understood this one. We'll meet in the next video. Thank you.